Hello everyone. Uh, my name is Grigor Mukurchian, and today our discussion is going to about the reactions of the benzene and the substituent of the benzene. So the first I will introduce talk about what's benzene. Benzene is an organic compound with the chemical formula of C6H6, which has the corresponding structure. The cyclic carbon atoms, which are their conjugated double bonds, and we can draw the corresponding resonance structure where all these double bonds can shift it to the neighboring bonds, and are forming the resonance structure of the benzene molecule. However, my favorite way is to write its resonance hybrid structure, which is just the benzene, and we have a circle at the end. So the benzene is a cyclic. So first it's a cyclic compound. Two, it's a planar. All carbons are sp2 hybridized. Three, they have a conjugated pi electrons, and in this case they have three of them. This is 1, this is 2, this is 3. And 4, they obeys the Huckel's rule of aromaticity. Because of all these four properties, therefore, benzene is an aromatic compound. Aromatic compound. The first, before going to talk about the reactions, I would like to talk about types of the compounds that are very common in nature, very famous in the commercial compounds, and the nomenclature of those compounds. And then we will start to talk about these reactions. So the substituted rings substituted, it's better to say substituted benzene rings in commercial compounds. One of the example, such as we have the benzene ring, and we have this carbon NH2, the weight of this metal group. This is amphetamine, which is the appetite suppressant. Another famous compound is, most of the people might like this, methamphetamine. In publicly known as the meth. Another famous compound, such as it has carboxylic acid and ester. This is now acetyl salicylic acid, aka known as aspirin. And then there are more and more that are very commercial compounds. So as we can see from here, that benzene rings is influenced in a lot of things that are very useful, somehow it's not. But we are surrounded by the things that the benzene ring has a big influence on. So now let's talk about the naming, the nomenclature, naming. So the nomenclature, naming are the same thing. So let's say naming the monosubstituent benzenes. Monosubstituted benzenes. Some of them are just adding the name of the substituent to a benzene. For example, if I have a benzene ring, one of the hydrogen is replaced by bromine. This is known as the bromobenzene. Similarly to the chlorine, if I substitute the chlorine, it will be chlorobenzene. There's another compound that you're gonna find, so it's called a nitrobenzene. Or just when you substituted a carbon chain, which is an ethyl benzene. However, there are some substituents. Some monosubstituent benzenes have the names that incorporated the substituent. So, for example, some monosubstituents, let me write that, some monosubstituted benzenes have name that incorporate the substituent. For example, the benzene ring substituted by methyl group. This is known as a toluene. The benzene ring that's substituted by the hydroxyl group, this is known as a phenol. Benzene ring that's substituted by the ammonium is called the aniline. And then we have benzene ring substituted by sulfonic acid. This is just sulfonic acid. There's a lot of them. I will just complete because they are very common. So they are like methoxide substituent. This is called the anisole. There's another like CH double bond with CH2. This is known as a styrene. And this is where this is useful to synthesize the polystyrene using the polymerization reaction. And then we have like benzaldehyde, benzoic acid, and then how many steps? Oh, I can fit those. I can fit more, I guess. This is the benzoic acid, and I can fit one more. Let's say the cyanide group. So this is called the benzene. Benzonitrile, apologies, benzo and nitrile, benzonitrile. There's a two things that we have to consider the groups. If we have a benzene, if we have just directly substituted to our benzene group, I'll put a dot so you don't mess with the methyl group. This is known as a phenyl group. So when you substitute alcohol, become a phenyl. It's just a part of phenyl group. But if you substitute it adjacent like a CH, another carbon, and then you substitute there, this is become a benzyl group. Benzyl group. This is kind of sometimes because, especially in conceptually, when in experiments, when they're describing like the compounds, like this benzyl group or this phenyl group, like this phenyl compound and benzyl compounds, you have to just kind of have the basic structure so to understand and to not mix up, especially if you're writing the reactions of the corresponding reactions that you're going to experiment on. So let's and another nomenclature that I would like to talk about is the alkyl substituted benzenes. Alkyl substituting benzenes. So in this case, let's say I have a benzene ring substituted dimethyls. So now I have a propyl group, right? 1, 2, 3. So this is a propane, and I substitute on the second carbon. I can call it this is a second propyl benzene, or I can just call it isopropyl benzene. The common name of this is known as a cumin. It's known as a cumin. Now let's say I have another substituent. Now I substituted the benzene, the butyl group. So let me just throw it VAG. So this is gonna be my priority. So this is my first priority, second priority, third priority, and it moves into counterclockwise direction. So this is like a S butyl benzene. S-butylbenzene. So let me just write 1, 2, 3, and let me just throw the tiny error so to know where we got our S, just the name, the S in our nomenclature from. Another substitute, let's say we have tertiary carbon. So this is a tertiary. So we have one. So there are 4 carbons attached to. So I can write this as a tertiary butylbenzene. Tertiary butyl group. And then there's like a easiest one, like let me just lower it down. This is like one. So we have 1, 2, 3, 4, 5, and we're using the lowest as possible. So the second one, so we have 2. Now we attaching to only directly to the benzene ring, so it's gonna be phenyl to phenyl, and now our carbon chain is pentane. 5 carbon chain, so it's a 2-phenyl pentane. And then similarly, if we attach it to here instead of here, so if we attach it to our benzene ring here, and forgetting about this, now it's become 3-phenyl pentane. However, as you can see, what's happened on the toluene, like we substitute alkyl substitute, but the toluene was also alkyl substituent. But why we didn't have a specific name like methyl-toluene and etc.? Because, like chemists love to say, there are many exceptions, and toluene is the one of the exceptions. In this case. Now let's go to our topics that we are considered on. How benzene reacts. So on our first, we're gonna consider the electrophilic aromatic substitution reactions. So this is known as, I'll put in red, AAS, because of the AAS reactions. So the most basic reactions is when we have our benzene group, right? Our benzene group is act as a the double bond act as a nucleophile, and it reacts with our electrophile, and it's a mostly forward reaction. It's a favor to forward than a reverse direction, and it just substituted directly our electrophile. So from one of the hydrogens, it just substitute our electrophile and plus the hydrogen cation. This is where the aromatic compound benzene undergoes. What kind of reaction that undergoes? However, there's a sigma complex and the intermediate, carbocation intermediate, because during these reactions, while it reacting to the electrophile, it produces the carbocation intermediate. So the mechanism is the following. the mechanism is the following. We have the benzene ring. I will draw those double bonds. So, the double bonds act as a nucleophile and attack to create a bond with the electrophile. And it's a slow reaction. So the intermediate, the carbocation intermediate. So in this case, now let's say this double bond, let's say, causes to create a bond between this carbon and our electrophile. So leaving this carbon, so which causes to leave this carbon electron poor, less electron. So this carbon become a positive and become a cation. So it become a positive cation. So I have my Y, I have my hydrogen, and it still keeps its aromaticity because the positive still, it's a planar. Now, I can draw the resonance structure. Drawing the resonance structure by just translocating the positive charge around the cycle. So now our new intermediate has these double bonds parallel to each other, and we have this positive charge here. And again, this we can shift this double bond to here, and we're left with, so where was it? Here, and we have this positive charge here, still keeping. So this is our carbocation intermediate. And this complex is known as a sigma complex. I don't know why they call it sigma, but it calls a sigma. And after undergo into this intermediate, there's a following to the fast reaction. So there's a fast reaction occurs, where in the case, the base, I will just draw the different, the base attacks to grab this hydrogen, and this hydrogen restores the aromaticity in a benzene group. So yielding our substituted benzene. And plus, we can say like hydrogen, some base, plus. Okay. So now I will just generalize the names of some of the reactions, some of the electrophilic reactions. So I will just write the examples of electrophilic aromatic substitution reactions by simply drawing the benzene group in the center. Okay, and I'm gonna react it into different. So there's a one reaction that will cause me to just substitute the bromine atom. So I will just rewrite this as the bromination the reagent that requires for bromination is our bromine gas in the presence of the aluminum bromide. Similarly, for the chlorination, during the chlorination, where just instead of bromine, I just substituted a chlorine. And the reaction name is called chlorination. And instead of bromine gas, we require the chlorine and aluminum chloride. Aluminum chloride. Another reaction, I will just write it here, is the nitration, which our product has a nitriso group substituted. This is called nitration, where it requires the 50-50% of the mixture of nitric acid and sulfuric acid. Nitric acid and sulfuric acid. Another one is the sulfonation. Sulfonation. Which just substitute our sulfonic acid which is just the fuming of sulfuric acid. And then another two reactions that I would like to include, where we get alkyl group substituted, which is called alkylation. And we have another one. What the fuck? Where our substituent is the acyl group. This is called acylation. All of these reactions are electrophilic aromatic substitution reaction. Specifically, these two are known as the Friedel-Crafts reactions, such as the Friedel-Crafts alkylation or Friedel-Crafts acylation. So let's start to talk about bromination and chlorination. Bromination or chlorination. Bromination and chlorination. So, however, most of the times, as you can see, we're using the aluminum bromide or aluminum chloride. At the same time as useful, instead of aluminum, we also use the ferric ion, which is the iron 3+. So the reason is because both of these reactions requires Lewis acid catalyst. Lewis acid catalyst. The reason, because the benzene the benzene's aromaticity causes to be less reactive than an alkene. Than the alkene. Okay. So both the example of the Lewis acids, such as the aluminum chloride, iron chloride, aluminum bromide, or ferric bromide. So the mechanisms for this reaction, I will just show the bromination. So the same applies to chlorination. So we have our bromine group. I will draw the lone pairs so it's easier to make sense of our reactions. So, and I will draw our R3. So in this case, our two lone pairs of these bromine atoms attract and reacts with the iron to form the bond between this bromine and the iron. So I will just draw how the reaction happens. So it reacts with the Lewis acid. Now the following, it just forms bromine 2 iron bromine 3. So in this case, the bromine loses an electron. I'll just draw the lone pairs. This bromine loses electron, so it becomes a positive charge, while the iron here gains electron. It gains the electron to one of its empty orbitals, and it becomes a negative charge. Now this corresponding bromine, becomes better electrophile, and this entire compounds becomes the better leaving group. Becomes a better leaving group. So why is this important? Now because we are reacting with our electrophile, so now our benzene ring it produces zwitterine ion. Now, since this is become a better leaving group, a better electrophile, so our double bonds attacks, well, this causes this to become a good leaving group. Becomes a good leaving group. Now, and it undergoes our sigma complex with the carbocation intermediate, and it becomes just now the hydrogen and the bromine. Now there's some base that might mix it up in this solution, but instead of the base we can say, oh, this the one of the bromide ion, because now this bromide ion, corresponding bromide ion, can now becomes electron rich and can take away the electrons to become in the stable form. That base is the corresponding base that we talk about is the bromine that comes and grabs this hydrogen and makes this double bond. Let me just makes this to restore the aromaticity. Now we have our substituted benzene group, and now we have the side products such as the bromic acid and also the iron ferric bromide. So the bromine, the negative charge of bromine, becomes a more stable. It becomes a stable cation form, a stable anion form, because it has the same electron configuration as the noble gas. Now, so as we talk about the Lewis acids, we can also talk about how does the Lewis acids have formed. So, the electrophiles adds to benzene ring. So, now, at the base in reaction, mixture, so the base in this reaction, such as this bromine, removes the proton from the carbon that bonded to the electrophile, Now, the corresponding catalysts that have formed for bromination and chlorination. So we have the iron reacts with our bromine gas to form our iron ferric bromide. So if you balance this, it will get, so this is will get 3, this is will get 2, this is will get 2. And similarly for chlorination, so it's become 2 few ferric chloride, and these three are known as our Lewis acids that were used to react for our bromination and chlorination. Because the interesting detail that our ferric halides react readily with the moisture in the air. They are generated generated in reaction mixture from our iron fillings and the bromine or the chlorine. So this is all about that you need to know about our bromination and the chlorination. Now, does this similarly applies to the iodination? The iodination is quite different. Iodination is quite different. Iodination of benzene. Iodination, due to its large electron cloud and ability to form like a stronger the iodine base, you need different reagents that will help the iodine to be substituted in our benzene reaction. So the general reaction is this. The iodine in the presence of the hydrogen peroxide and the sulfuric acid, where your iodine substituted and you have the hydrogen ion plus. Now, in this case, is the bromine our iodine is the electrophile? No. Our iodine first reacts with our hydrogen peroxide and sulfuric acid to generate our electrophile iodine plus, which will undergo electrophilic substitution, the sigma complex reactions, to form our substituted benzene ring. So the electrophile, the generating electrophile reaction is the iodine reacts with our hydrogen peroxide plus the sulfuric acid. It forms the electrophile, the desired electrophile. It also produces the water and bisulfite anion. We can balance this reaction by just two hydrogens. So there's two iodines, so here there's two, and we have 4, so there's a 2 here, and there must be another 2 here. And then therefore, I can just write following the sigma complex. Therefore, it forms our iodine, our substitute reaction. There's no need to rewrite this complex again, because as long as you generate your desired electrophile, everything becomes the same path to form our substituent reaction. So we talked about the bromination, chlorination, and iodination. And wait a minute, it seems like I forgot to include iodination here. So now let's talk about the next one, which is the nitration. In the nitration, the general one, is the benzene ring reacts with the nitric acid, the presence of sulfuric acid mixture, and there must be a 1-to-1 ratio to form our substituent group NO2, which is, and plus the water, which is the side product. And as you remember from here, that it's a nitrobenzene, which substituted our nitrile group, nitronium ion, into our reaction. So how does our electrophile generated? So we're going to do simple reactions to understand how does that happen. So first, our nitric acid and this is our positive charge here, and reacts with the sulfuric acid, drawing these Lewis structures of these acids. So it takes a while because I forgot. Now, because of their pH differences, our nitric acid in this reaction acts as a base, while the sulfuric acid acts as an acid. In this case, these corresponding oxygen acts as our nucleophile, which attracts deprotonate our sulfuric acid. So it grabs the hydrogen over there and causing this electron to drop onto this oxygen, and it yields this intermediate. Now, in this case, we can do some resonance where our oxygen forms the double bond, causing this to become a better living group, since this group is become a living group. If I do this resonance, dropping this lone pairs onto here, this will cause, instead of going from here, it will cause this to leave the group. This oxygen, these electrons are responsible for this one, drops onto this oxygen, and it becomes our water as the side product. Therefore, our reaction produced our electrophile while keeping the positive charge on the nitrogen, and this is known as the nitronium ion plus the water as the side product. And again, therefore undergoing the sigma complex, therefore it forms our substitute nitrobenzene group. Okay, two more left, and then we are done. We will do more examples in the future videos. So for right now, let's sulfonation. In the sulfonation, the general reaction is the benzene rings react with sulfuric acid So in the presence of the heat, which is called a fume, this is the fuming of the sulfur trioxide gas, that will cause to substitute our sulfonic acid into our benzene, and the side product is the water. So let's see how does this happen. So the sulfuric acid reacts by itself So in this case, one of them acts as an acid, one acts as a base. So in this case, this oxygen attracts to this hydrogen and causing these bonds to drop onto this oxygen, causing to form our positive charge plus our bisulfide anion. Now we care less about our bisulfide anion because we have to create our electrophile, which is not ready yet. So how does that happen? It's just this bonds drops onto here, that causing this to go left to this group. Now this forms this intermediate, I'll just draw the hydrogen here, but these bonds can go onto here and it becomes positive charge drops onto the sulfur atom, and this is where our electrophile generated, and this is called the sulfonium ion. And in our sulfonium ion, it reacts with water, the living group, and this forms the double bond, and therefore it produces our sulfur trioxide with H3O plus. Let me rewrite that. It produces our sulfur trioxide plus our hydronium ion or hydroxonium ion, and then again undergo the sigma complex. Therefore it forms our I can draw the entire structure, or I just can simply just write as 3H. You can just simply think of that just either our carbon group is attached to here that causes there to form this complex. Okay, let me just draw it a little bit bigger. And here we go. The next future videos, I will talk about more about the Fiedlercraft acylation and alkylation, because I separately want to indicate that one, because there are some specific details I want to talk about it. For now, today, this is all it. So you have learned about some nomenclature, basic nomenclature, the importance of the benzene group, why it's about the aromaticity, and the reactions of the benzene group. So thank you so much and have a wonderful night. Thank you.